Hello, today we'll be solving problem 1.12, part A, from Griffiths' Introduction to Quantum Mechanics. So it starts off by saying we're dealing with a harmonic oscillator from problem 1.11b. The information we were given from that problem, if you search back to that question, is that V of x, the potential energy, is equal to 1/2 kx squared. So now let's start with part A. So part A is asking us to find the probability distribution for P, for momentum. So basically, how we can find this is that we can say the probability that we get a certain dp. So the probability that the momentum is a certain value in the range of dp is equal to dt over t. Now, this makes sense because we're basically saying that the probability that the momentum is a certain value, like dp, is the amount of time that the momentum is that value divided by the total time. So, for example, we can draw a quick graph right here. And then we can make this axis P, and let's just make this axis T. Now, let's just say our momentum looks a little bit like this. And so we can say this is T1, and this is T2. And let's say this is the specific momentum value we want to focus on. Let's just call this P1. Basically, we're saying that the chance, the probability that the momentum is this P1 is, so it's within this dp, is the same as this dt all over t. So the amount of time that the momentum is at that value divided by the total time. Now we can rewrite this as dt over dp times dp over t. And now what this equation is saying is that for each dp, we have a certain dt. We have a certain amount of dt's per dp. So for some dp's, you might have a very small amount of dt, which is meaning for this dp, you have a very small amount of time. So that means you have a very low probability. But for other dp's, you might have a lot of dt's per dp. You might have a lot of time for that dp, making it a higher value, a higher probability. Now, dt over dp is just the reciprocal of dp over dt. And we know dp over dt is equal to the time derivative of mv, because momentum is equal to mv. Now we can do product rule to find what this is, which is equal to dm dt times v plus dv dt times m. Now we're assuming mass is constant, so this is 0. So dp dt is equal to dv dt is just a acceleration, a times m, which is equal to force from Newton's second law. So we can say this is equal to dp over dp dt times t, which is equal to dp over t times force. Now, the force is not a constant in terms of p. It actually relies on p, because remember, force is equal to dp dt. So the value of p changes the force. So this force is a function of p. Now, we can go on, and how do we find the force? Well, we know that force is equal to negative dv dt, and if we look up here, we see dv dt is 1/2 kx squared. Oh, and sorry, this should be x. And this would cause negative kx, which is a Hooke's law. Now, we know that force is a function of P, because when we want to find the probability that P is in a certain range, we'll need to integrate over here, over that certain range to find the probability. So if we want to find f of P, we see that K is a constant. That means X is a function of P. So different momentums will lead to different X values. Now, how do we find X of P so that we can find F of P? Well, we can use conservation of energy. Here we know the conservation of energy is equal to the potential energy plus the kinetic energy. And this will be equal to 1/2 kx squared plus 1/2 mv squared. Now we can try to isolate for x, but first we need to see that there's no p in this equation, but we know p is equal to mv, and we see something similar to mv. So we can actually rewrite this equation as 1/2 kx squared plus 1/2m p squared. So we can say that 1/2 kx squared is equal to e minus 1/2m p squared. And then we can multiply, so x squared is equal to 2/k e minus 1/2m p squared. Or x is equal to plus or minus the square root of 2e over k minus 1/mk p squared. And then we can multiply by negative k to get the force, because we can see here from this equation. So f of p is equal to minus plus k square root of 2e over k minus 1/mk p squared, which is equal to minus plus square root of 2ek minus k/m p squared. So now we can have our probability function. We can say that the probability of p times dp is equal to, and if we look up here, it's equal to this, dp over f of p times t. And then we can rewrite this as dp over t times minus plus root of 2ek minus k/m p squared. Now, let's see, should we take the negative or positive square root? If we draw what the situation might look like, we can model the situation with a spring connected to a mass that's oscillating back and forth. So if sometimes it might compress here, and then when it compresses here, it'll have all that potential energy and it'll go back and stretch out. So it'll just keep moving back and forth, back and forth, back and forth. Now, if we take the positive square root, we're saying force is positive. Now, force is equal to negative kx. So force is positive. If k is a constant, force is positive when x is negative, because the negative in front of the k will cancel out with the negative value of x and cause a positive force. So if we say that over here is the point where there's no potential energy, where we can say x is equal to 0 here, is the equilibrium point, then we can say that over here, x is negative, so force is positive here. Now, let's just say the spring is just to the left of this x equals 0 point. So that means the velocity is this way. But if the velocity is this way, that means the velocity is negative. And if the velocity is negative, that means the momentum will be negative. And then it'll keep going here until it's at its maximum compression and then go back. Once it's going this direction, the velocity is positive. It's going closer to the positive side of the x values. So that means the momentum is going from negative to positive, which makes sense because if we say that dp over dt is equal to f and f is positive, momentum will go from a low value to a high value. The derivative is positive. So we can easily take the positive square root k minus k over mp squared. We can take the positive square root and make sure that every time we integrate, we go from a low p, so p low, to p high. If you want to take the negative square root for the force, we'll just have to do the opposite. Go from a high to a low momentum. And that is part A. Thank you for watching.